Hello, this is Chris, aka VamFun on the Vex Robotic Forum. I'm going to show you three videos. The first one is a introduction to a PTC monitor that I've developed over the summer, and the next two videos show the effects of a robot being installed with and without the monitor. As you recall, a PTC is a positive temperature coefficient resistance device that when a current flows through it, it will heat up and start from a value of R0, which is the reference resistance, and it will increase slowly as temperature increases until it reaches a critical temperature, which for our PTCs is around 100 degrees C. Once it gets above this temperature, the PTC becomes extremely nonlinear and the resistance increases very fast. It feeds on itself, and the hotter it gets, the more resistance, and the more resistance, the hotter it gets. Eventually, it shuts down the motor. Where I'm pointing to here is an area where we'd like to never exceed. So if we can regulate the temperature of a PTC so it stays below 100 degrees C, we can then keep it from tripping. This figure shows a PTC temperature versus time for two separate currents. A stall current of 4.8 amps is a curve that sets a target temperature for the PTC, which will start at 25 degrees and head toward with a time constant of tau, and eventually it'll steady state out. And the second curve on there is a curve which has a lower current, which is what I call a safe current, where the PTC will stabilize at a temperature just under the critical temperature, and this way it essentially is equivalent to the hold current for a PTC. As long as you have that current in there, the PTC will never trip. Okay, now that we've got the fundamentals down, essentially the monitor that I developed acts very much like a thermostat in your living room that controls a heater. There's a T sub M, which is the set point of the thermostat, and it's typically set at about 90% of the critical temperature T sub C. In this way, before you cross T sub C, you will trip this level, and it will cause an action to be taken, which will change the current or change the heating value, such that the heat is lowered and the temperature no longer rises. If you maintain a stall condition, then the temperature will be regulated very close to the setting on the thermostat, as you can see. And this would be like if you maintained a 0.9 amp safe current in a 393 motor. If the 393 is allowed to move and the encoder begins to pick up speed, then the command can be reduced, and it will come off of the regulated level and approach, let's say, curve 3. And this allows the PTC to cool, which means that you've got a current demand that is less than the 0.9 hold, and therefore, since there's less current, the temperature will drop slowly according to the time constant of the PTC. This is a great feature. So once it's cooled, then the monitor allows you to once again pull full current. So here's a picture of the structure of the monitor. The user creates a robot command just like it would normally feed to a motor, and with the PC in a non-engaged or non-tripped mode, the command is fed directly to the motor. This is inserted in between what you would normally find from the user and the motor. I've created a current limiter that is built-in software that will automatically examine all the motors that are being commanded and examine every port and how the ports are connected, and it will combine the currents such that they create the exact current that will feed each of the higher level PTCs in the Cortex and the power expander. And if there is a trip, as shown on here, the logic will switch the switch to the safe command. The safe command in turn is generated by an iSafe current, which is preloaded along with other necessary data from the PTC parameters that were distilled from the specs. In addition, we need data from the robot user, the ambient temperature T0 and the threshold T sub m that they're going to control the temperature to on the PTCs. Also important is the current, and this is generated from current models that were developed over the summer based on test data, and we have a pretty good handle on this now, and it requires only the command and an encoder speed for each of the motors that are being used in the monitor. Okay, I want to say a little bit about the models before we leave the subject. Here is a graph that shows a curve fit of a simple model to actual test data taken in a lab by James Pearman. This is for a Cortex PTC and HR 16-400, and it basically shows how long it takes to trip if you start from 25 degrees C and add a current and hold it for a certain period of time. The dark blue line is the test data, and the other lines are showing the effect of varying the time constant tau, which essentially regulates how fast a PTC will heat up. And if we vary this, we can change how well we fit the model. In general, we want to be on the turquoise line, the lower line, as opposed to the magenta line, because it will be more conservative in terms of how well protected we are from tripping the actual hardware monitor. What this says is that if we use the turquoise line, that will trip a little bit sooner than normal. In other words, the internal software monitor will heat up quicker than the actual hardware monitor, and it will put you into a current regulation mode sooner than you normally would. But this is okay. It keeps you from ever tripping the PTC, and the only disadvantage is that you'll have a slightly lower average current from your regulation than you would if you had a better match to the model. But it's the price you pay for having uncertainty in the models, and we'll live with it. And basically, we still have a good timer that is very reasonable to adjust. We can take it in on the day of competition, run the robot into a wall, stall the motors, and see if the PTCs trip. If they don't, we can raise our temperature level a little bit until they do. And once they do, then we back off a little bit, and you're good to go. Okay, we're ready for some testing. Unfortunately, there's no sound on the motors, so you'll have to go by my voice and watching the axles. You'll notice my cat is supervising all the work, and the chassis is a trophy bot that I use for a Segway. It's on its side. It uses 4-inch wheels. It has two 393 motors that are high speed, 160 RPM. The voltage on the motor that we'll be using is about 7.2. The encoders are quadrature, and that provides the motor speed, and the Cortex channels 1 and 2 are driving the left motor respectively. Channel 1, which is a 2-wire, and channel 2, which is a 3-wire, driving a motor controller 29. All the current for both motors must be supplied by a single PTC, which is located in the Cortex, and in turn each of the motors has their own PTC. So there's 3 PTCs involved, and we would expect either one to blow depending on the time constant. So the first test is with the no monitor engaged at all. I will turn on the motors and start them going, and then disengage the monitor and then install the wheels. So right now you see the wheels are turning at 160 RPM. The axle is turning. I just shut off the monitor, and now I'm going to stall the wheels and watch them. And if I stall them and let go, the wheels still move because I haven't overheated the PTCs yet. I'll stall them a little bit longer. They're still moving. I take the book under, and you can see the wheels have some torque enough to drive it into the wall. Now I've held it long enough that the PTCs have now tripped, and you can see that the robot has gone to sleep, and it will stay asleep until 1 or 2 minutes, and you're essentially out of the competition. If I lift it up and take the load off the wheels, there's still a tiny bit of current, and the wheels will begin to turn if I give them a little help. Once they begin to turn, the motor begins to cool the PTCs, and you regain some torque. Right now the motors are running pretty fast, and they've got enough torque to do something. They're sitting on the book. When I stall the motors again, they will overheat, and now the motor's gone to sleep, and once again they have stopped. So this is a very undesirable situation, and it's happened to a lot of my teams during autonomous, where a robot will run into a wall and they'll be dead for the rest of the tournament. So the next test, I've engaged the PTC monitor, which is a software monitor, and we'll see what happens now. Okay, the motors are running at 160 RPM. I stall them for a little bit. They start up right away. No PTCs have stopped. Stall them for a little bit more. They still run right away. The motors are propped up on a book right now. Again, I stop them for longer. As you recall in the last test, this would have tripped the PTCs and the motors, but they're still running. My software monitors have tripped. They have reduced the current limit to 9/10 of an amp per motor. But this still allows full RPMs of the motor, and you can see that if I continue to stall the motors even longer, that's about 4 or 5 seconds, I've still got about 20% of my full torque available to run, and I'll stall it even longer, and this for sure would have stalled the motors without the monitors working. But the current limiters are now set at basically the hold level current for the PTCs, and therefore the PTCs can run almost forever without tripping. The temperature internally on my monitors is roughly about 90 degrees. As I lift this thing up and the motors run, it cools down the PTCs, and I'm watching the temperature slowly drop, and when the temperature gets down to about 81 degrees, I re-engage the full current limit, which means that you can now again pull 4.8 amps. If, once again, the motors are stalled, the amount of time you have before that current monitor re-engages will depend on the differential temperature available. You can see right now I've got the almost full torque. I do have the full torque available, and I'll stall the motors again, except for my battery, which has fallen out. Okay, now I'm stalling the motors, and once again the temperature is heating up. The PTC monitors have engaged. I have again now 9/10 of an amp per motor, which gives me enough to get out of trouble, and still stay in the match. And if I keep off the throttle, these PTCs will be allowed to cool as the motors run a little more freely. I can stop individual motors no problem. It will take care of the PTC on each motor individually. If I stop the motors in pairs, it will tend to heat up the PTC that's in the Cortex. You can imagine if I had 4 motors, that if I stall all 4 of those, then the first monitor to go would be the PTC monitor. In this case, I only have 2 motors, and the time to trip for a single motor is about 3.6 seconds, and the time to trip for a Cortex monitor with 2 motors stalled is about almost 5 seconds. So what's happening here is when I stall these 2 motors, the Cortex monitor is still available for use for anything else. The only thing that's happening is the motor monitors are tripping. Okay, I've presented some limited testing of a new concept of a smart current limiting using PTC temperature models. Based on what I've seen, it appears very feasible, and likely we'll see it in the future robotC programs. The robotC model is very user-friendly and can be inserted in between the user command and the motor port function. The setup is automatically allocates the correct motor current models and PTC models for the monitors. This is a very good feature. The motor command is given to a structure array instead of the motor port. That's the only change the robot programmer has to do. This is a very user-friendly. Now there are different strategies you can do if a PTC monitor trips. I have a default strategy that current limits the minimum number of offending motors or motor that are involved in the PTC trip. The user can choose to prioritize various functions. For instance, if a drive motor stalls, the user may want to lower currents that are being drawn for less priority functions such as a lift, and this way you can maintain higher currents on the essential motors. Or you may want to limit currents symmetrically as opposed to asymmetrically. Okay, my special thanks to all you forum members that have helped out, especially James Spearman of Team 8888. For helping with the current and the PTC models. Have a good day. See you all in the forums.